Hello and welcome to a short video. This time this is very much aimed at my year 9s where they seem to have got this question. It's such a nasty one, asked in their like a little revision booklet for algebra, and it is really very difficult, so I'm very happy to go through it. I want to talk first about why your approaches were wrong, because it was a noble effort, it really was, but there's a couple of slip-ups in both of these approaches, so we'll talk about those. Then I'm going to talk about how I tried to do it, and I'm going to show you my first approach, which kind of failed ish, and then my second approach, which kind of worked, but I made an assumption which I think should be clear in the question if they indeed want you to solve it in this approach, but it's still a very difficult approach. Okay, so we've got Jim and Tim sharing money. If I square Jim's money and add on Tim's, I get 10 grand and 50 pounds. If I square Tim's money and add on Jim's, I get 2,600. How much do H have? Well, I completely agree with your framing of the problem that J squared plus T is 10,050, but J plus T squared is 2,600. Absolutely, yeah? Now, I also agree with what you've done here. You've thought, well, I really need a J squared in this first one, so I'm going to square everything, yeah? There's nothing wrong with you doing this, and I did a similar approach when I did it, yeah? So you did that. The one place you went wrong was when you went down to this line. You made the cardinal sin of squaring this and squaring this, but that's not how it works, because if you do a little grid, you'll see that J plus T squared times by J plus T squared equals, sure, you get a J squared and you get a T to the 4, just like you said you would get, but you also get a JT squared and a JT squared, in other words a 2JT squared. So you're missing two terms there. Remember, you can't square 5 plus 3, yeah, if I try and square 5 plus 3, that's 8 squared, which is 64. You can't do that as 5 squared plus 3 squared, yeah, so that's not the way you square out brackets, because that equals 34, so, you know, it clearly doesn't work. So yeah, don't do that, basically, and that you've made that mistake there, and you've also made it in this one, when you've gone to a squared here, because when you've gone like you're squaring this line, yeah, so you need to square 2,600 minus t squared squared, and that's going to give you 2,600 squared, sure, but then it's going to give you minus 2 times 2,600 times t squared, and then plus a t to the 4, so you're missing a middle term there. So that's why your approaches didn't work and failed, yeah. I think it's always important to see what the mistake we're making is as well, yeah. So let's talk about how we can do it, and the answer is, well, unless you're given an extra piece of information, definitely not analytically. What you might try is very similar to what you were doing. You might think, okay, well, I've got t equals and I've got j equals here, and I could kind of plug it in and square it, yeah? So I tell you what, let's take your first approach, yeah? You did this, yeah? Well, what you could then say, oh, but then again, we can still have j's and t's. So what I'm going to do is I'm going to try, it's a similar approach to your second approach, though. I'm going to try and eliminate t from the second equation. Well, j, let's do j. If I rewrite, if I call this a and b, and I rewrite b as j equals 2,600 minus t squared, then I can plug this value of j in here, yeah, into a. Plug into a. And this isn't the way to do it really, but let's show you why, what happens exactly. Let's decide why it's not the way to do it. Okay, we get this, yeah? Now you could square out 2,600 on your calculator. I can't remember what it comes to. I think it's, here it is, 67,600,000, which is pretty ugly. Have I got enough zeros there? No, there we go. Minus 2 times 2,600, which is like 5,200 t squared, plus a t to the 4, plus a t, equals 10,050. Yeah, and I could take it all onto this side and write it as a quartic, because it is a quartic, minus 5,200 t squared plus a t, and then I'd write it plus 6749950 equals 0, and then I could use something called factor theorem, which we do in year 12, and factor theorem is just like a guessing theorem, and I could guess at solutions. That's definitely not the way to do it, because this is for year 9, yeah? Now, I'm not saying my next approach is like obvious to year 9 students at all. I'm going to do a really crafty way, so that way let's just consider it as a kind of a bit of a lost cause and give up. So I'm going to try a new approach. My new approach is going to use this idea. I'm going to assume that j and t are integers, yeah? And this is should only be done if j and t are definitely integers. Then this approach will work. But I think they should say that in the question to give you even half a chance of getting this, yeah? Assume j and t are integers. Then what have we got? We've got j squared plus t is 10,050. And j plus t squared is 2,600. Well, what I could do is I could subtract, couldn't I? And I'll end up with j squared minus t squared plus t minus j equals 7450. Minus t squared there. Yeah, and then I could use the difference of two squares and factorise this. That will give me j plus t, j minus t. And then I could have, I'm going to change this to minus j minus t. Purely so, and I hope you can see that as the same as plus t minus j, because I get a minus j, I get a plus t, it's the same as that. Now the reason I'm doing that is I've now got two brackets which are exactly the same, so I can factorise again. And I can take out the common j minus t, and then make the other one. Well, I need to times the j minus t times by a j plus t, if you like. That times that would give me that. And then times it by a minus 1 in the end, because that times that gives me this. Now, this trick only works if you know that your answers are integers, yeah? And I know that my answers, well, I don't know that for sure, but money normally is, you know, they're probably talking about wages with integer solutions here. So if you know you've got integer solutions, this could work. And what you could do then is we could do a prime factor decomposition on 7450, yeah? Now, 7450, you can see that it's definitely divisible by 50, and actually you need to do 50 times 149. Yeah. Now what's really nice here about, I've only partially factorised it here. I haven't turned 50 into 2 times 5 times 5. But I don't really need to, because if I know that 7450 can be written as a factor pair like that, especially because I know that 149 is prime. Yeah. Wow. Well, that's really useful, because it means that one of these needs to be my prime factor. Yeah. Because this is a number which is, you know, this number clearly can be factorised, and, you know, we can factorise it into 50 times 149. Now, which one of this and this is bigger? The right-hand side one is bigger, because I'm doing j plus t here. So I can say, so, j plus t minus 1, that needs to be equal to 149, or in other words, let's simplify it, j plus t is 150. And j minus t must be your 50. Now we can solve these simultaneously by adding them together. 2j is 200, and so j is 100, and plugging it back in, you can see t is going to be equal to 50. And you can check that this does indeed solve the original equation, as I did, and you've got 100 squared, 100 squared plus 50, that is 10,050, and if you do 100 plus 50 squared, well, 50 squared is 2,500, plus 100, you get 2,600, yeah? And there you go. That is the end of that problem. That's a very difficult question. What's up, Bibbins? So my daughter's crying. She's obviously seen how menacingly difficult that question was. Sorry we put that on the end of the Year 9 algebra, because that definitely is extremely tough. I also floundered at first and made it a quartic, and then thought, well, I can't need that. And then I thought, oh, if I subtract, I've got difference of two squares, and I can do that provided I know that the final values are integers. What do you want, Bibbins? You want the car? Or do you want the robot monkey? No. No? Would you want the skateboard? No? Okay, I better talk to my daughter now. Well, thank you for listening. I hope that helped, Jamie. Honestly, monstrously difficult question. Yeah, really tough. But well played for having a go. Good for you. Okay, bye-bye.